Hello everyone. Today we're continuing with the DBE November 2022 Physical Sciences Paper 2, that's Chemistry for grade 12. We're continuing with question 3. Questions 1 and 2 have been done in previous videos. So today we're going to look at question 3. Okay, the melting points of some organic compounds are given in the table below. Alright, we have propanon, butanon, pen-2-on, 3-methylbutanon. Alright. To which homologous series do the above compounds belong? Alright, so let's see. Well, they all end in the same suffix, O-N-E, and we know that that comes from ketone. That's where the suffix O-N-E comes from, and they're all, they're all the same. So the answer to 3.1.1 is ketone. All right. The melting point of the compounds A, B, and C are compared. Write down the controlled variable for the comparison, for this comparison. Okay, so of course, they all have different melting points, as you can see here. So what is being controlled? So when you have an experiment, you can't change more than one variable. There has to be a variable that is constant, or else you can't compare the things in your experiment. So in this case, the thing that's in common is all our species under investigation are all ketones, all ketones. So the controlled variable in this experiment would be the functional group. Okay, the functional group is the same in all of them, and that means doesn't matter what the carbon chain is. That side we have this functional group, doesn't matter what it is this side. Okay, we're all dealing with the same functional group. Okay. All right. Okay. 3.1.3. Okay, so comparing the melting points of C and D. Fully explain the difference in the melting points of these two compounds. Okay, so usually for this question you would just answer in words, but it does help to draw first. Let me draw in blue. Okay, so C is pen-2-on. Okay, that means I'm gonna draw using sticks. So it's a sort of shorthand. So pen, so we have 5 carbons, 1, 2, 3, 4, 5. And then it doesn't matter how we count, the ketone group is on the second carbon. Okay, and then our second one is 3-methylbutanon. So 3-methylbutanon. Okay, so we have butanon. So our stem is 4 carbons long. 1, 2, 3, 4. So we actually drew an extra carbon. Let's get rid of this last one. Okay. So 3-methylbutanon. So the reason why we don't say which carbon the ketone is when we say butanon, we just say butanon, is because no matter which way you count, if we put it here and we count, this is 1, 2, 3, 4, it can go there. What if we put it the other side? Okay, so instead of putting it there, what if we put it the other side? Well, if we put it the other side, put it over here, we can't put it anywhere else. If we put it on the ends, it becomes a aldehyde. If we count again, 1, 2, 3, 4. So regardless of which way we do it, it's always on the same carbon. If you remember in the previous case, maybe it'll help if I draw it. It was here, and we count it this way. It's the same carbon. Even if you more correctly go 1, 2, 3, 4, and 1, 2, 3, 4, it's still carbon number 2. So that's why we don't put the number that it's on when we draw this, because it's always on the same one. Okay, so let me just draw it again. I'll just put it here. So this is carbon number 2, and then on carbon number 3 we have a methyl. It should just be like that. Okay, so now the question is asking us to explain fully the differences in the melting points, okay, between these two compounds, okay, C and D. And we can see here that compound C has a higher melting point of about -77, and this is -92. So this melting point is higher. And why is that? So longer chains, branch chains, or anything like that basically cause a larger surface area over which the intermolecular forces act. So this has a much lower melting point because the intermolecular forces are actually weaker. Okay, this branching means that the intermolecular forces are weaker, and that's why this one has a higher melting point, because it's just a straight chain. Okay, so the molecules can pack much closer together and therefore have a strong overall intermolecular force, intermolecular forces of attraction acting. So there's a couple of reasons. So the first one you could talk about is the structure. Okay, that's the long chain versus the branching. Next, you would have to relate that structure to intermolecular forces, how the structure impacts the intermolecular forces. And then finally, you have to relate the idea of these forces to the amount of energy required in order to melt these materials. And when you relate it to energy, you can then explain the difference in temperatures observed. And that's how you would answer this question. So you have to structure your answer in a methodical way that answers the question. It helps to draw things out so that you can see the differences, but of course, in the actual test, you don't have to do that. You just write your answers out, be clear. So 3.1.3, like we said, structure, intermolecular forces, energy, relating this to temperature. Okay, good. Let's move on to 3.2. The table below shows the results obtained from an experiment to determine the vapor pressure of different straight chain primary alcohols at 300 Kelvin. Okay, define the term vapor pressure. So this one, you just have to know this. Okay, how can we define it? So what's important is that there are many different ways you could lay out your answer. You just have to have the key phrases. So an example answer would be the pressure exerted by a vapor at equilibrium with its liquid in a closed system. So that's like some definition you could find in a textbook, but the key idea is that there's some pressure from vapor and it's in equilibrium with the liquid and the system's closed. Because of course, if it was an open system, the vapor would just escape into the atmosphere, and eventually you'd have nothing left in your container, so there wouldn't be any pressure as the vapor is escaping. So key ideas is pressure and equilibrium, and closed system, and that will get you the full marks. Okay, so question 3.2.2, write down a suitable conclusion for this investigation. So let's have a look at our results and see if we can surmise anything. Okay, so initially we have a vapor pressure of 16, okay, and we have a primary alcohol. Well, I suppose we don't know. I guess all of them could be primary, so that doesn't matter. But we basically have methanol first, right? 1 carbon, and then we have 2 carbons, and the pressure drops from 16 to 7, then 3 carbons, and it drops again, 4 carbons, it drops again, 5, it drops, 6, it drops even more. So I think a decent conclusion from this, okay, would be as the alcohols get longer, or you could say larger, and if you want you can talk about molecular mass, then you can say as that happens, the vapor pressure decreases. And that's a fair assumption. That's a fair conclusion. Another way of saying it, vapor pressure decreases with increase in number of carbon atoms, chain length, anything like that. Rephrase it differently, but the idea is as the molecules get longer or larger, or there's more carbons in the molecule, the vapor pressure drops. Okay. Last question. Write down the IUPAC name for the alcohol with the highest boiling point. Okay. So, the alcohol with the highest boiling point is the alcohol with the lowest vapor pressure. Okay, that's the first thing you need to be able to get from this. So what does that mean? That means lowest vapor pressure means it needs the most energy to boil or turn into a vapor. So this has the highest boiling point. Okay, and this is what we have. So we're going to make a couple of assumptions here. We're going to assume it's a primary alcohol and there's no branching in the chain. I think you have to make a couple of those assumptions. So let's see. Okay. So 3.2.3. So we have C6, H13, OH. Okay, so assuming a straight molecule, no branching, and assuming a primary alcohol, we are gonna have something 1, 2, 3, 4, 5, like this. That's our molecule. So we have 1, 2, 3, 4, 5, 6 carbons, and then our OH group. And we can see that the stem for this is hex because we have 6 carbons and it's an alcohol, so we know the functional group is all. And we've assumed it's at the end, so you can say 1 hexanol, or you can say hex, dash 1 dash all. All of these work. Yeah. And if you really want to get technical, you can also just say isohexanol. It also just means the same thing. You don't have to put a capital H. You can can put a small h here. Isohexanol. But I would say the easiest and most correct one would be this one, but these are also technically correct. Okay, both work. All right, let's have a look at the last question. The experiment is now repeated at 320 Kelvin. Oh, okay, so we didn't note this, but initially the experiment was done at 300 Kelvin. And just for reference, if you want to convert this back into something we're used to, like degrees Celsius, you would just say minus 273.15, which gives you like about 26 or 27 degrees Celsius, this temperature, okay? And now they switch to 320 Kelvin, which you just add another 20 onto that, so this is like now at like 46 or like 47 degrees Celsius, so it's a little bit hotter. Will the vapor pressure of each compound increase, decrease, or remain the same? Okay, they end with a tricky question. So what you got to realize here is that if we have our container and our alcohol, and there's a whole bunch of atoms that make up our alcohol, and then we have some vapor coming off here. Of course, it's a closed container, so we have our vapor coming off here and collecting up here. How easy it is for the vapor to come off and increase the pressure here depends on how much energy these atoms in liquid have. So if it's hotter, I'll just draw some heat. If it's hotter, there's a higher average kinetic energy in all these molecules. So it's easier for them to go off into vapor, and that therefore increases the pressure. So basically, to answer the question, at increased temperature, the vapor pressure also increases. And that concludes question 3.